All right. Well, welcome everybody. Good evening from the Princeton area to all of you locally and spread out across wherever you may be. And welcome to our speaker tonight. Here's the agenda. We're going to go through a few announcements. I've got a couple of things to bring to everybody's attention. But then in really short order, we'll turn it over to Victor, our program chair, and he'll introduce the speaker for the evening. And we'll take as long as our speaker desires, but typically an hour for the presentation and some questions after the end. We have plenty of time built into the evening, so there's no problem with that. We'll ask members to hold questions until the end, and then we should be able to get through them. And then after that, we'll take a quick break and then come back and do astronomy by and for members of the club. And that will kick off with our journal club presentation by Surabhi tonight. She's got something very interesting from her travels to bring to us. And since we are an astronomy club, we do real astronomy, and springtime, of course, is always galaxy season for us here in the Northern Hemisphere. A great time to see more galaxies, many of which are Messier objects that are here on this sky map. This is really a naked eye view. Looking straight up in the middle of this on the purple line, the meridian is the zenith. And so you can see the distribution of the blue ovals. These are representing the positions of galaxies that can be seen with telescopes such as the one the club is running out at Washington Crossing Observatory. And this is the best time of year to see a large number of these galaxies, that great cluster around the constellation Virgo. Just zooming in on this a little bit more, Virgo in the lower left there, you can see the Virgo cluster, and then to its right, Leo, and some of the really famous Messier objects, for example, M66 and 65. And as you guys know, I can't resist showing you an astrophoto or two. So here's a picture that I took from my own telescope here in my yard in central New Jersey of Messier 65 and 66, the galaxy pair in Leo that's so famous, and something that we can actually see. Doesn't take a deep sky camera to pick this up. This is visible through the eyepiece as well as through video cameras with our telescopes, and really a beautiful demonstration of what I'm talking about, the number of galaxies. One other that's a beautiful one that I just did actually this week, the Tiger's Eye galaxy up in Ursa Major is another example of a face-on spiral that just presents itself in all its glory. Both of these are something we could do. Maybe if this weekend pans out, we are going to have our next monthly Astro Video group session. A Zoom link will be sent to all members. One of your benefits of being a member of AAAP is you get to join in these sessions. It's a way for us to try to bring real observational astronomy to club members, whilst it is difficult for you to get out to the observatory because of the COVID stuff. We're going to bring astronomical observing to you. And so with that, enough with our local stuff.
I want to welcome tonight's featured speaker, Keivan Stassun, Stevenson Professor of Astrophysics at Vanderbilt University. His presentation is entitled The Royal Road, Eclipses and Transits in the Era of Gaia and TESS. Professor Stassun will discuss the ways in which eclipses and transits of stars by their companions, utilizing light curves from the NASA TESS mission and parallaxes from the Gaia satellite, can be used to determine the fundamental properties of stars and characteristics of their planets by the thousands, and with a precision never before possible. A few words about our speaker. Professor Stassun earned undergraduate degrees in physics and astronomy from UC Berkeley and a PhD in astrophysics from the University of Wisconsin-Madison. He was a NASA Hubble postdoctoral fellow before joining the Vanderbilt faculty in 2003. Professor Stassun's research on stars and exoplanets has appeared in more than 350 peer-reviewed journal articles. He's a co-investigator for the NASA Transiting Exoplanet Survey Satellite, or TESS, mission, and is the founding director of the Vanderbilt Initiative in Data-Intensive Astrophysics, through which his group participates in the Sloan Digital Sky Survey and other large-scale collaborations. Professor Stassun is an elected fellow of the American Physical Society, the American Astronomical Society, and the American Association for the Advancement of Science. He has received recognition for his scholarship and his teaching, including a career award from the National Science Foundation, the Cottrell Scholar Award from the Research Corporation for Science Advancement, and was recently named Mentor of the Year by the AAAS. Professor Stassun is a national leader in initiatives promoting diversity in astronomy and space science. The Fisk Vanderbilt Masters to PhD Bridge program, which he founded, has become one of the nation's top producers of PhD to underrepresented minorities in the physical sciences. He has served on the NSF Committee for Equal Opportunity in Science and Engineering, and is a recipient of the American Physical Society's Nicholson Medal for Human Outreach. Professor Stassun recently launched the Frist Center for Autism and Innovation, focused on advancing science and engineering through the engagement and advancement of individuals with autism.
All right, so should I just jump in then?
Absolutely.
Okay, great. Thank you again. It's a real pleasure to have this opportunity to be with you. What I thought I would do is go through this just incredible revolution that we're experiencing in astronomy and astrophysics due to the advent of the ability to measure the light curves of stars by the tens or hundreds of thousands with exquisite precision, first with the NASA Kepler mission and now more recently with TESS mission, together with the ability to measure the parallaxes, the distances of stars by the millions, also with exquisite precision. Combining these surveys of very large numbers of stars across the sky is allowing us to put these data together in clever ways to measure the fundamental properties of stars and of the things that orbit them, whether they're other stars or planets, with really tremendous precision and in very large numbers. So this is what I wanted to share with you today. And I referred to this topic as the Royal Road Redux because one of my favorite lectures that has been documented is that by Henry Norris Russell of the Hertzsprung-Russell diagram fame. Russell also happens to be my academic great-great-grandfather. And he gave the inaugural Russell lecture in 1946 at Radcliffe College. And he titled that inaugural lecture named after him, and that continues to this day, The Royal Road of Eclipses. And I'll just read to you sort of the beginning of this. From immemorial antiquity, men have dreamed of a royal road to success, leading directly and easily to some goal that could be reached otherwise only by long approaches and with weary toil. Times beyond number, this dream has proved to be a delusion. The easy way has ended in an impasse, and the right track has led up the hill difficulty. This has been so invariable in experience that the very suggestion that there might be a royal road is hardly to be mentioned in polite society, whether of scholars, statesmen, or saints. In the larger sense, this distrust is fully sound. We cannot expect nor hope to get at anything worthwhile without working for it. Nevertheless, there are ways of approach to unknown territory which lead surprisingly far and repay their followers richly. There's probably no better example of this than eclipses of the heavenly bodies. He goes on to talk about how this advent of the study of eclipses of stars will lead to great astrophysical riches. So, and so I agree with my great-great-grandfather. And so what I'm going to do is describe to you not only stellar eclipses, as in eclipsing binary stars, but of course now a kind of eclipse that we refer to as transits is that of the transits of stars by transiting exoplanets. In both cases, stellar eclipses and exoplanet transits, we can now combine to do really fantastically precise astrophysics. Okay, so that's the context, and that's why I chose the title that I did. So a few years ago, my colleague Willie Torres at the Harvard Smithsonian Center for Astrophysics and I realized that there were now a large enough number of quote unquote benchmark grade eclipsing binaries, about 150. By benchmark grade, I mean eclipsing binaries where the stellar properties, the masses, the radii, the luminosities, the temperatures, et cetera, had been determined empirically to very high precision, such that we could actually infer the distances to those eclipsing binaries with sufficient accuracy, that we could actually test the accuracy of the trigonometric parallaxes available for them. And the way that this works is that because with eclipsing binaries, as you probably know, from the eclipse light curves and the orbital velocities, we can measure with very high accuracy the radii and the temperatures of the stars, and therefore their bolometric luminosities with high accuracy. We can also now measure the bolometric flux at Earth of these systems using broadband photometry spanning from the UV to the IR. I'll show you what I mean by that in a second. We can infer the distances with a precision of just a few percent, and that's because if we know the bolometric luminosities to say 10%, this simple mathematical expression leads to, if you have a 10% bolometric luminosity measurement, then that implies that you have a 5% distance measurement. Typically, we can do even much better than that. Why would we want to use eclipsing binaries to infer distances to test trigonometric parallaxes? You probably know that the Hipparcos mission from a couple of decades ago, which was fantastically important for direct distance measurements of stars in the solar neighborhood, got the answer notoriously wrong in one very important case, and that was the distance to the Pleiades, to the Seven Sisters. Hipparcos recorded a trigonometric parallax distance of about 120 parsecs, where every other method known and used had estimated the distance to be quite a bit larger, almost 140 parsecs. We used a newly discovered eclipsing binary system in the Pleiades to demonstrate that this approach of using an eclipsing binary system, measuring the bolometric fluxes and using the known radii and temperatures and so on, allowed us to estimate a distance to the Pleiades that was in accord with all of the other estimates, and that indeed proved that the Hipparcos measurement was wrong. So now we have the Gaia mission by the European Space Agency. And we thought, since we know that Hipparcos got the answer to one star cluster wrong, at least, now that Gaia was coming out with parallax measurements to stars and clusters across the galaxy, we could use these eclipsing binaries to make sure that Gaia was not having the same kind of problems that Hipparcos had. So here I'm showing you just a handful of the 150 eclipsing binaries that Willie and I studied, where what you're seeing here is what we call a spectral energy distribution. You're seeing the measurement, the flux measurements from Earth at wavelengths spanning the ultraviolet all the way out into the mid-infrared. And for each of these systems, we can infer the total bolometric flux. By bolometric, I mean spanning all wavelengths. The total flux of the two stars combined in the eclipsing binary with very, very high accuracy, because we have these measurements. We can model those measurements using the known emission properties of stars, and we can even then correct for the interstellar extinction or absorption that changes the observed fluxes and infer the true intrinsic fluxes. We can do all of these corrections in a totally empirical way. And the result from this study that Willie and I did is that the typical uncertainty we can achieve, the typical precision we can achieve in the bolometric fluxes is a couple of percent. And the result is that we can infer the distance or the parallax to a given eclipsing binary with a typical precision. The units here are micro arcseconds with a typical precision of about 100 or 200 micro arcseconds. So this is fantastically good precision in the parallax that we can infer. And so what that allowed us to do was to basically test initially whether Hipparcos had problems beyond the Pleiades. And the quick answer is that we found good agreement, with the exception, the important exception, but with just the exception of the Pleiades, we found good agreement in the Hipparcos parallaxes to within 1 or 2 standard deviations for the entire sample of eclipsing binaries. And what's really important is that because the precision that we can achieve with these eclipsing binaries doesn't degrade with the distance to the eclipsing binary, that means that we can therefore use these benchmark eclipsing binaries to test the distances or the parallaxes of Gaia, even out to quite large distances, a few thousand parsecs in some cases. So as soon as the Gaia mission delivered its first tranche of parallaxes, Willie and I applied the eclipsing binary benchmark technique to the first data release, the DR1 parallaxes from Gaia. And we found that there was, in fact, a systematic error in the first data release of Gaia parallaxes at the level of about 260 micro arcseconds, or about 1/4 of a milli arcsecond. Now, I should say, this is actually a good sign from the standpoint of the Gaia mission, because the Gaia mission in its very first data release stated in their documentation that they expected that there was a systematic offset in their parallaxes as large as about 1/3 of a milli arcsecond. They weren't sure what sense that systematic offset was, were the parallaxes too large or too small. So basically what we demonstrated with these eclipsing binaries is that, as the Gaia team expected, there was an offset of as much as 1/3 of a milli arcsecond. We quantified it to be about 1/4 of a milli arcsecond. And moreover, we showed what sense that offset was. So this allowed users of the Gaia parallaxes to have confidence in the veracity of those parallaxes, and to be able to apply this small but quantitatively precise correction to those parallaxes. So that's good news. The point being that eclipsing binaries really do what Henry Norris Russell told us they could do. They can be fantastically precise benchmarks. Now I want to turn to what we can do, not with eclipses, but with transits. So a former postdoc of mine, Karen Collins, she's now a scientist at Harvard, and Scott Gowdy, who's a professor at Ohio State, we wrote this paper where we basically laid out a methodology where you can use the eclipses or transits of planets across their host stars to, again, enable highly precise measurements of the properties of the stars and of the planets. And so here's how this works. So there's a lot of math gobbledygook here. Let me just summarize it for you. What do you have when you have a star, and the NASA TESS mission has measured the light curve of a planet transiting in front of it? What all do you have there? Well, as I showed you a moment ago, you can construct the full spectral energy distribution of the host star. Here's an example. From the ultraviolet to the mid-infrared, we can measure very precisely, as I showed you, the bolometric flux of that star across all these wavelengths. And because we have that bolometric flux, and if we have a measure of the temperature of the star from a spectrum or from color or from a spectral type, we can combine the bolometric flux that we measure empirically, the temperature from the spectral type, to get the angular radius of the star. That's basically what I showed you a moment ago, right? That precision of like micro arc seconds. If we then combine that angular radius with a parallax from Gaia, now we can turn that angular radius into a physical radius. So we now have the ability to measure the radii of stars very directly with these bolometric fluxes and spectral types and parallaxes. But then now we also have, in the case of a transiting planet system, we have the transit of the planet across the face of the star in the TESS light curve. One can express the properties of the observed transit in the light curve, the transit duration, the transit depth. You can express that in a way that basically you can represent as the mean density of the star. That's some math that was initially demonstrated by Sarah Seeger and colleagues. So if I just told you that I can measure the radius of the star from its angular radius and parallax, if I know its physical radius, and now because I have a transit, I also have the mean density of the star, well, I can combine the radius of the star and its mean density to obtain its mass. So the point is that I can use the transiting planet as a probe of the mass of the star that it orbits. And you probably know that masses of stars outside of eclipsing binaries are in general very difficult to measure precisely. Well, here we have a way to measure the masses of the stars precisely because we can measure the radius precisely because we have precise parallaxes and because we have these hyper-precise light curves of transits of planets. We can then, of course, turn around the stellar radius and mass by virtue of the planet transit to infer the planet's radius and the planet's mass. So the royal road of eclipses or of transits that Russell referred to, we can now actually extend not only to the stars, but to the planets as well. And just to kind of give you a sense of what's possible, what we showed in this initial methodology paper that Karen and Scott and I wrote is that the typical angular radius precision, look at this plot on the right, the typical angular radius precision that we can achieve for typical planet hosting stars is like 2 or 3 micro arc seconds. Okay, this is comparable to the angular radius precision that one can achieve with the world's most cutting edge interferometers. Like you've probably seen these images of like Betelgeuse or Arcturus that have been made with interferometric instruments. Those instruments, which are like cutting edge tour de force instruments, typically achieve angular precision of a few micro arc seconds. We can now do the same thing without an interferometer, just by virtue of the fact that there is a planet passing in front of the star and combining the information in this clever way. And so the result, as we showed in this paper, is that even for stars out to distances of 100 parsecs or a couple hundred parsecs, we can achieve fractional precisions in the radii of the stars of a few %. And similarly, fractional uncertainties in the masses of the stars of a few %. And so here I'll pause to just remind you of what you may know already, which is that precisions of stellar radii and masses of a few % are typically only achieved with the most well-studied eclipsing binary star systems. Here now we can achieve that same benchmark eclipsing binary grade precision and quality with lots and lots and lots of non-eclipsing stars by virtue of the precision achieved with the transiting planet, the TESS light curve, the Gaia parallax, etc. And so I thought you might appreciate this. Certainly, I think Henry Norris Russell would appreciate this. This is a Hertzsprung-Russell diagram of known planet hosting stars where every quantity that's represented in this diagram, the temperature, the bolometric luminosity, the size of the symbols here represents the radius of the star. The color represents the metallicity of the star that we obtain from a spectrum. Every quantity represented in this Hertzground-Russell diagram, we measured directly and empirically. No theory, no assumptions, other than just that we know, how colors and temperatures relate to one another, and that trigonometry works. So I thought that was kind of cool. We also were able to show that we can totally empirically, no assumptions, find really interesting trends in the properties of the planets that orbit these stars. So for example, in this diagram on the left, the color coding relates to the amount of insolation. In other words, how much light from the host star impinges on the planet. And you can see that with these hot Jupiters, those are the planets up here at the upper right, they have radii of, sort of 1 to 2 Jupiter radii and masses of about a Jupiter mass. A planet of a given mass, say 1 Jupiter mass, will have a larger radius of up to a factor of 2 or so if it is more highly irradiated by its host star. So these are trends that we can identify in the data, again, in a totally empirical way without making large theoretical assumptions. So going forward, the TESS mission was designed to, where the Kepler mission, right, performed a large census of stars for planets in a kind of a pencil beam through the galaxy. The TESS mission was designed not to do a census so much as to identify the most promising planets for exploration within the solar neighborhood, right? The nearest, brightest planet hosting stars. And if you don't already have familiarity with the TESS mission, this diagram on the right, I think, kind of captures it nicely. So what you see here represented is a comparison of the Kepler planets in blue, the Kepler planet hosting stars in blue, and the TESS planet hosting stars in red, where the host star magnitude is shown on the vertical axis and the radius of the planet that's been discovered around that star is on the horizontal axis. And as I mentioned, Kepler was very, very important, but the vast majority of Kepler planet hosting stars and their planets were really quite faint. I mean, you really needed a telescope in space or, quite large telescope on the ground. In contrast, TESS is very complementary. In fact, the brightest of the TESS planet hosting stars are pushing naked eye, certainly, binocular and certainly sort of backyard telescope range. So TESS, I think, is a great successor to Kepler in the sense that it's, kind of democratizing. Kind of everybody can participate, and in fact, maybe some of you are already involved in some of the amateur professional collaborations around follow-up of TESS planets and their host stars. So I wanted to now extend this methodology that I've been describing to you of using eclipsing binary stars, of using planet transits across stars to measure precise properties of stars and planets. I want to extend this one step further, and this is now going even beyond the royal road that Henry Norris Russell imagined, to now do precision radii and masses of single stars, okay? So, what is it about eclipsing binaries that made them so great in Henry Norris Russell's imagination? Well, right, what eclipsing binary stars give you is that, one star is gravitationally interacting with another star. And right, ultimately, in order to measure the mass of anything, you have to measure its influence gravitationally on another thing, or the gravitational influence of another thing on it. And that's what eclipsing binary stars give you. That's what transiting planets around a star give you. But what if you want to be able to do this for just single stars, no other star orbiting it, no planet orbiting it? We now have a way. And the basic methodology goes like this. We measure the surface gravity of a star. In other words, its self-gravity by virtue of brightness variations, really subtle brightness variations on the surface of the star that we refer to as granulation, and that we can actually measure with a really precise light curve, such as that from Kepler or TESS. We take that star's self-gravity, the surface gravity, and combine that with a precise measurement of a stellar radius, measured the way that I've already described to you. Put those together, now you have a stellar mass for a single star without reliance on having another thing orbiting it. To explain how this surface granulation-driven brightness variation measurement of the surface gravity of the star works, I'm going to show you a quick video that was produced by the journal Nature when we first discovered this, this method. So hopefully this will work. Oh, I just realized you're probably not seeing the video right now, right? Is that correct? You're not seeing the video?
We're not seeing it yet.
Okay, give me 1 second. I just realized I have to share the video and not the slides.
Yep.
Okay, you see it now?
Yes.
Okay, and I hope the sound will come across. Okay, I'll spare you the rest of the elevator music there, and let me get back. Oops. Okay, am I back on the slides? I hope.
Yes.
Great. Okay, so the video there emphasized, well, it emphasized a couple of things. Partly it was emphasizing this kind of neat sonification of the light curve data, but it was also emphasizing the application of that granulation Hiss methodology to measuring the properties of stars and thereby of the planets that orbit them along the lines of what we've been talking about already. What the video doesn't emphasize, but what I want to emphasize here, is that physically what that granulation driven Hiss, or brightness variations from the Kepler and TESS light curves really measuring is the stellar surface gravity. And just like on the surface of Earth, right? The surface of the Earth has a surface gravity of 1g. Surfaces of stars have surface gravities. And that surface gravity is basically the ratio of the mass to the radius. It's actually to the radius squared. But anyway, you have the ratio of the mass and the radius in that surface gravity. The granulation-driven brightness variations, or Hiss, tell us the surface gravity. And so if I measure the radius, now I have a way of measuring the mass. And so this is just to show you how good this surface gravity stellar flicker method works. I'm showing you in this graph a comparison of the surface gravity. We usually write this as log g for historical reasons, showing the surface gravity of stars that we measure through this granulation flicker method on the vertical axis versus the surface gravity that's been measured for a sample of stars asteroseismically. It's another method, kind of a gold standard method. And this is just to prove to you, I mean, this is obviously a fantastically, basically perfect correlation. This is just to prove that the granulation flicker method is able to very accurately and correctly measure the surface gravities of stars. And so, again, using this methodology of spectral energy distributions, right, measuring the bolometric fluxes of stars over a large set of wavelengths, we can measure the angular radius of a star. Here, by the way, I've already shown you this, but these numbers are interesting. This shows that the angular radius that we infer from this spectral energy distribution bolometric flux method agrees perfectly with the angular radii that have been measured interferometrically for a couple of benchmark stars. Again, just to show we're getting the right answers for the angular radii of these stars. And so when we combine the bolometric, the spectral energy distribution, SED, bolometric flux together with the Gaia parallaxes, as I showed you before, we get the radius of the star. We can compare those radii to the radii of stars that are measured astroseismically. Again, the correlations are perfect, so we know we're getting the right answers. And so then finally, combining those radii with the granulation flicker-based surface gravities, we get the masses of the stars. And at the moment, those masses that we measure through this methodology are not super precise. You see the scatter here of 26%. That's basically because with Kepler, the granulation signal that we can measure, which we can definitively measure, gives us a very precise measure of the surface gravity. By the time you turn that surface gravity together with the radius into a mass, the uncertainties kind of compound or add up. And with the Kepler measurements, we were ending up with a precision of the stellar masses for these individual stars, mind you, precision of the stellar masses that was not, fantastic, 25% or so. But with TESS, I don't have a graph to show you, but with TESS, and we're working on this now, we expect that we'll be able to achieve a precision in the stellar masses that's 2 or 3 times better than that. And so the result of all of this, and this is work that's underway, and this is basically what I promised to tell you at the very beginning, is that this is what we expect to be able to achieve within the next couple of years as the TESS mission begins to complete. We'll be able to combine all these data, apply these methods that I've told you about to measure the radii of stars with few percent level accuracy for about 100 million stars in the galaxy. We'll be able to measure masses of 1 million or so stars to this sort of not fantastic, but still pretty good accuracy of 25%. For a subset of those stars, tens of thousands of them, I mean, this would blow Henry Norris Russell's mind, right? 10% accurate stellar masses without requiring another star orbiting, without requiring a planet orbiting it, individual stellar masses for tens of thousands of them with precisions of 10% or better. So this is just a revolution. And so this is sort of the end of the story. In the era of Gaia and TESS, we have these precise, accurate, and empirical measurements for thousands, if not millions, of planets and stars. And so we'll really be able to usher in this era that my colleagues and I refer to as precision stellar astrophysics and precision exoplanetology. Something that Russell could only have dreamed of. Actually, probably wouldn't even have dreamed of it because transiting planets weren't known at the time. And so I thought I'd end as I began, with homage to Russell. He ended his lecture, and I'll end this one with his words. This talk has been no complete guidebook to the Royal Road. At best, it may have given a glimpse of some of the profitable realms to which it leads, and some good reasons for an increase of traffic on it. And so with that, I'll thank you for your attention, and I hope you learned something there. This is obviously something that I'm very interested in, and the next couple of years, we're just going to see more and more of these great advances, thanks to TESS and Gaia and other missions coming down the road. So I hope I didn't go on too long, and I'm happy to take a few questions if you like.
Professor Stassun, I've heard that the TESS project was going to act as a finder scope to the Hubble Space Telescope. How will that actually work out practically as far as the mission of the James Webb Telescope?
Yeah, good question. So as I mentioned, right, whereas the purpose of Kepler was to give us a kind of statistical understanding of the commonality of planets of different types, the purpose of TESS was to identify specific planets around specific nearby bright stars, so that with the James Webb Space Telescope, we will be able to know, okay, that 6th magnitude star, we know, thanks to TESS, has a transiting planet. We know, thanks to TESS, that it has a roughly Earth-sized transiting planet. What James Webb will therefore be able to do is to confidently point at that star, and even to know exactly at what time to point to that star, because we know when the planet is transiting in front of it, in order to be able to measure the properties of the atmosphere of that planet, using the method of transmission spectroscopy, and so on. So, James Webb Space Telescope time is so valuable that you wouldn't want to just point Webb at some star and kind of hope that there was a planet there, or hope that you're getting the timing right. TESS basically tells us which stars, which nearby and bright stars, and at exactly what time to point Webb to do the atmospheric characterization.
Professor Stassun, I wanted to ask a question about, I know you're active in promoting, people on the autism spectrum to participate in scientific research. I'm assuming that might have had an impact in analyzing your Kepler data. And I'm interested in hearing more about that story.
Yeah, yeah, you put your finger right on it. So the way that we made that discovery with the Kepler data of the surface granulation being encoded in the Kepler light curves, and that encoded in turn the surface gravity of the star. That discovery was made by members of my research team who are on the autism spectrum. And even though the video that I showed you kind of took a little bit of creative license in terms of the sonification of the data, you know, in truth, we did the sonification of the data for the purpose of the nature video. The reason that we did that is because the autistic members of my team who were involved in that discovery explained how their visualization of the data kind of had a multi-sensory character to it, right? And this is something that you may have heard in the, you know, that you may have heard about some people with autism will, you know, will hear things that, you know, that most of us would describe as seeing. Or there's a famous mathematician who's on the autism spectrum who talks about doing math in color. So this is a very interesting kind of multi-sensory aspect that not all, but many people with autism experience. And what we found is that in some cases that actually gives them the ability to have a kind of insight into the information content of data that many of us might otherwise miss.
When you're seeing variations in brightness caused, as you say, by granulation, I mean, it's hard to imagine that these even space-based telescopes have the angular resolution to discern that. What is it you're actually looking at?
Yeah, okay, great question. So in the nature video, you saw an image, or a time-lapse image of a star with surface granulation and star spots and so on. That was our own sun, right? So, right, with our own sun, we have the angular resolution to be able to literally see the granulation happening in real time. And that's been known for a long time. For basically no other star in the sky do we have the angular resolution to be able to make images or let alone movies like that of the sun. What we can do with a number of other stars, maybe couple hundred other stars, is we can perform a technique that we refer to as asteroseismology, where the stars are bright enough. There's only a couple hundred stars in the sky that are bright enough to do this. The stars are bright enough that we can measure in the light curve. It's not we can't resolve the surface of the stars, but in the light curve of those stars, we can perform a spectral analysis for a Fourier decomposition to analyze the various frequencies of oscillation of the star. That's the asteroseismology. And with that very detailed oscillation frequency analysis, you can determine the surface gravity of the star and various other quantities. And that's a technique that's been done, as I said, for a couple hundred stars over the last couple of decades. Very, very difficult to do. What this granulation method does with a Kepler or a TESS light curve of another star, again, we're not resolving the surface of the star. We're not seeing the granulation. But what we're doing is we are measuring the very, very low level variations in the light of the star that's due to this flickering effect. We don't resolve the image, but in the point source combined light of the star, we nonetheless can measure the flickering. And the analogy that I use is, imagine you had a pot of boiling water on the stove, okay? As the water boils, you get these churning motions, right? These convection motions of the water boiling. That boiling motion, the convection of the water in the pot, causes the pot to vibrate with a characteristic frequency. And if you could measure that characteristic frequency of vibration of the pot, it turns out you would be able to infer the size of the pot and the density of the material it's made out of. That's very hard to do. It turns out what we showed with this discovery is that you don't actually have to measure the full vibration of the pot. If you can measure the sound of the roiling water in the pot, you basically can get the same information. And that turns out to be, it's much easier to measure the sound of the boiling water than to measure the high frequency vibration of the pot. So where asteroseismology measures the vibration of the pot, the star, this granulation signal is measuring the sound of the boiling water at the surface. That's the analogy. But again, just to be very clear, with the exception of the sun, we're not resolving the surfaces. These are all measurements that are being made by virtue of light variations, subtle light variations that we measure in the light curves. I hope that made any sense at all.
No, that was helpful. Thank you.
I'd like to ask a question while others are thinking of their questions. To what extent does the proper motion of stars create like confounding situation when you're talking about the Gaia data and other parallax measurements? Because it seems to me that would be a nightmare to sort out.
The answer is sometimes, and sometimes quite spectacularly, but almost never. And here's what I mean. The absolute proper motions of the vast majority of stars in the sky are really, really quite small. Now, Gaia has the precision to measure those proper motions and to measure them accurately. But the absolute amount by which the vast majority of stars in the sky, detectably move such that they might start to get confused with some other nearby star, the amount that they move, the absolute amount of proper motion, typically very, very, very tiny. We're talking about, so a typical amount is like 1 milli-arcsecond per year.
But I thought you were talking about micro arcseconds in your data.
Yeah. So the micro arcseconds that I was talking about is the angular size of the star itself. So we're able to not resolve, but infer the angular sizes of the star at the level of 1 or 2 or 3 micro arcseconds. The proper motion is the amount by which a star is moving across the sky. A typical number there is like 1 milli-arcsecond per year, such that for a typical star, you have to wait 1,000 years for it to move 1 arcsecond on the sky, right? Now, there are a few spectacular exceptions to that. Barnard's star, which you might know has the largest proper motion of any other star in the sky, has moved so much. Its proper motion is so large that over the course of Gaia's, couple years of operation, it actually has, basically people have to manually keep track of it in the Gaia data because it moves so hunkin' much. But there aren't very many stars like Barnard's, so.
Thank you.
Oh, one question. Could you explain again, I was confused about one of your first points on how you used eclipsing binaries to infer parallax. And
Okay.
I realized, I think sort of late, that when you say parallax, you do mean distance. But
Yeah.
I just, by the
Yes.
time I realized that, I didn't understand how that worked.
Yeah, no, that's right. I was maybe being a little bit sloppy with my terminology there, just for expedience. But so indeed, what I meant there was distance. And the way it works is that, right, if you have an eclipsing binary star system, and this is what Henry Norris Russell was talking about. If you have an eclipsing binary star system, from the eclipse light curve, you basically measure the radii of the two stars. If you have radial velocity measurements of the two stars from spectra, then you measure the masses of the two stars. From colors of the stars or spectral types of the stars, you basically have information about the temperatures of the stars, right? So for a standard eclipsing binary analysis, you have the radii of the two stars, you have their temperatures, you have their masses. And because you have, in particular, because you have the radii and the temperatures, you might be familiar with a physical law sometimes referred to as the Stefan-Boltzmann law, which basically says that the radius squared times the temperature to the fourth power tells you the luminosity of the star. Okay, so because you know the radii and because you know the temperatures, you therefore know the luminosities of the stars for these eclipsing binary stars. If you know the luminosity, the intrinsic luminosity of the star, or the two stars in the eclipsing binary, and you can measure the bolometric fluxes of the stars at Earth, basically by measuring their magnitudes from the UV to the infrared, now I have a measure of the intrinsic luminosity, the apparent brightness, and now I can just use the inverse square law of light to infer the distance. So indeed, with the eclipsing binary stars, what we're really able to infer via the intrinsic luminosities and the apparent brightnesses is the distance. What I then took the next leap to say was, if I know the distance, I can tell you what the parallax would be. And that is what we can compare with the parallax measurements from Hipparcos or Gaia to test whether Hipparcos or Gaia are getting the right answers. Does that help?
Oh, yeah, thanks a lot. Also, the part about knowing the orbital velocity from the spectra, it didn't occur to me, and that ties it all together.
Yeah, okay.
So it seems to me that part of what you're saying is that you have a new and incredibly prolific way of devising standard candles. I mean, is that part of what you're doing?
That's a perfect way to say it. Eclipsing binaries. Well, and this is not new. I mean, another way of saying what Henry Norris Russell was saying in that 1946 lecture is that eclipsing binaries are a kind of standard candle. What we've now shown, going beyond what Henry Norris Russell was talking about, is that individual stars can be not only standard candles, but they can be standard, what would be the word? Standard scales, right? We can measure the masses of individual stars through this really pretty, amazing technique of using the star's self-gravity, as it were, together with its radius. There, we just coined a term, standard scales.
That's great. We learned a lot. Thank you very much.
Great. A real pleasure. Great to meet you all.
Really terrific you joined us tonight. And we'll let you go here. Once again, thank you.
Hi, everyone. I'm Surabhi Agarwal, and you may know me as the co-editor of Sidereal Times. So today I'm going to talk about, yes, today, do you see just one screen or you see two screens?
Two. One screen.
One with the map of India.
Okay. So a couple of years ago, I visited my hometown of Jaipur, and I visited the observatory there. These are masonry instruments, and they were built by Maharaja Savai Jai Singh II. He was the ruler of Rajputana state within the limits of the Mughal Empire in the 1700s, 1600s, 1700s. Now, Maharaja in Hindi means the king, and Savai literally means 1 1/4. That's the title given by Mughal Emperor Muhammad Shah II, who recognized the brilliance of Jai Singh. This is a statue of Jai Singh very close to my grandmother's place. The Jaising was coronated at the age of 11 after his father's untimely death. He continued his studies with his princely duties. He was a brilliant student, and his mother engaged the best tutors who taught him religion, philosophy, arts, and architecture, town planning, also. So he got intensive training in mathematics and astronomy. He read the master works of Aryabhat, Varamahira, Brahmagupta, Bhaskaracharya, all the ancient luminaries of Hindu astronomy. He was also taught from the Hindu treatise on mathematics called Surya Siddhant. Now, this is Amer Palace, and it was the Rajputana state's capital in the 1600s and early 1700s. It is built on the mountain range called Aravali. Now, Jaising, there's a picture of us within in the palace. Jaising founded the city of Jaipur in 1727 in the foothills of Amer, and he moved his capital from Amer to Jaipur. You can see the schematic diagram of Jaipur. It's one of the best built walled cities with 9 fortified gates, and the Jantar Mantar Observatory is right here in the middle, where within the city palace complex. So how did all this come about? How did these observatories come about? So in 1719, the Mughal Emperor Muhammad Shah II wanted to undertake an important journey. He asked his court astrologers to find an auspicious date, and each one came up with a different date in mind, and they did not agree on one single date. So at that time, Jaising highlighted the discrepancies in the JESS, that's the Islamic astronomical book. And he put forth the idea to bring more accuracy to astronomical calculations, hence the observatories. So he built 5 of them. He was an expert in Arabic, Greek, and other astronomical traditions. So Jaising was well aware of the large-scale brick and marble instruments that were built by Mirza Ulugh Beg of Samarkand in 1428. So it's currently in Uzbekistan. So he sent fact-finding teams to that area and to Europe to check the latest technologies there. And Jaising himself designed quite a few aspects of these instruments that he built. So they were built in Delhi, Jaipur. Delhi was the capital of the Mughals. Jaipur was his own capital. Mathura was the legendary city in Mahabharat epic. Varanasi was the seat of learning, and Ujjain was actually deemed as the Greenwich of India, or the prime meridian was established by the Hindu astronomers in ancient times. And these observatories were called Jantar Mantar. Jantar, from the Sanskrit word of yantra, means instrument. And mantra is to calculate in Sanskrit. So Jantar Mantar basically means calculating instrument. This is a picture of the observatory. Here you see the instruments, masonry instruments. This is the city palace. And behind the city palace, you see the Nahargarh fort of Jaipur. Jantar Mantar was named as the World Heritage Site by UNESCO in 2010. It has 19 big, large-scale instruments made of stone and brass and spread over 5 acres. And it can measure time. All these instruments can measure time, predict eclipses, map the orbit of stars, calculate distances between planets, and they were built without the aid of any computers. So they are now being researched with the help of 3D software, and they are pretty precise. This is the entrance to the city palace. inside the City Palace Square. This is the aerial view of the observatory. Here's another aerial view. And 3 systems were used to record positions of these planets, of the planets. There were, and stars, of course, the altitude and azimuth, the declination and right ascension, celestial latitude and longitude. And the recording of these positions of the planets was of utmost importance in Hindu astrology. This is the schematic diagram which shows all the different instruments. Now we'll talk about the next slide is actually pretty interesting. This one is the largest. It's called Brihat Samrat Yantra. Brihat means big, great, large. It's the largest sundial in the world, and it shows time to an accuracy of plus or minus 2 seconds. The height of it's a gnomon and quadrant basis of the instrument, and the height of this gnomon is about 22.6 meters, and the radius of 15.5. Edges are made of marbles. This is the quadrant, and the edges, it's made of marble, and so are the edges of this gnomon. So as the shadow falls, as the sun rises and the shadow falls on it, it tells you the time. And the pavilion on top of it was used to announce eclipses and monsoon rains. Now then this yantra, or this instrument, is the jewel of the instruments in terms of, it's just pretty to look at. And it's called Jai Prakash, which literally means light of Jai. This is actually the most intriguing yantra in Jaipur. It's a set of 2 sunken half spheres of marble, and they're non-identical twins cut out, and each marble cutting actually marks an hour. So the bowls are engraved in different maps, and these maps show an inverted view of the equatorial and altitude and azimuth coordinates used to point to the positions of the celestial objects. So looking at the shadow cast by this particular ring, which is in the tied in the middle, one can figure out the sun's position in relation to planets and stars. And it's just pretty. The next one is the Unathamsa yantra, and this is used to measure the altitude of the celestial bodies. And measurements can be made by mounting a sighting tube at the intersection of the cross beams of the circle, and aligning the sighting tube with the celestial body in question, and reading off the celestial scale on the circumference of this ring through a pointer attached to the sighting tube. So most of these instruments are in working condition. The next one is the Kranti with a instrument. It measures directly the celestial latitude and longitude of an object in the sky. And then this instrument, this particular one right here, it's called Nari Valya Yantra. It means basically the north-south meridian. And it is also quite an intriguing instrument. Here's a model at the bottom right. You see the model. It basically has 2 circular plates, one facing north and the other facing south, and a small nail-like rod at the center is it shows the shadow of it shows the apparent solar time of the place, and it is inclined at 27 degrees. So the southern plate is sunlit from autumn to spring equinox, and the northern plate from spring to autumn equinox. So essentially means that each of these plates it's function for 6 months of the year. So as you can see in this picture on the bottom left, the Sanskrit inscriptions on the southern dial. This is on the southern dial. it tells a story of conservation and renovation of this yantra. It's quite interesting because the first one tells you how Lord Ganesh is remembered. Then in the second one is the purpose of the instrument. The third one is the curiosity of the ancestor who built and acknowledged, it's acknowledged, and before getting into the details of the renovation. The next slide, this is the Raj Yantra. It's basically, it's an astrolabe, the left one. The right one, the purpose is not known. It's probably was never finished. So it has all the nakshatras or the, what you say, the zodiac signs marked on it. And its pillars are aligned to 23 degrees with the plane of the meridian. And it is engraved to work for a place having 27-degree latitude. That is the latitude of Jaipur. The second one here is the smallest of the instruments. This is called Dhruv Darshak, or it basically points to the North Pole. It's also inclined at 27 degrees, and it's probably the first instrument built here to set the direction for the rest of the observatory. This one at the bottom left, this is the great Rama Yantra, and it is made of two cylindrical structures, measures the altitude and azimuth of celestial objects, including the sun. And the platform right here, the circular platform, it's built of quartzite blocks in the Vedic altar fashion. And these small yantras were made before, they were made as models. And they are also functional. They tell that they're undoubtedly a little less accurate, but they also tell the same thing. They are also in working condition. And the next one is actually pretty interesting. It is it's a set of all 12 instruments, and it is each instrument refers to a sign of the zodiac. Each one has a gnomon and a quadrant to it, and each has a small painting of the zodiac sign. So the Capricorn is the steepest, and the gnomons gradually descend following the order of the zodiac. Like Pisces to Aries to Taurus to Gemini to Cancer, with Cancer being the one with the smallest angle, possibly just about 3 to 4 degrees. And then from there, the gnomons gradually ascend towards Capricorn. So as Capricorn starts from winter solstice, that's the day when the sun is furthest away from Jaipur, the steepest slope is assigned accordingly. And Cancer starts from summer solstice, the day when the sun is closest to Jaipur, and hence the most gentle of slope. That's us in front of each of the different instruments. And I will close with this beautiful, these two lovely pictures. This one, the first one on the left, is a view from Amer Palace, and it shows the water basin below. And in ancient times, it is said that they used to grow saffron. So I don't know what grows now, but something is growing. On the other picture, the other picture is taken from Nahargarh Fort, and it shows the Jal Mahal or water palace. They're beautiful pictures. And well, that's done. The last slide actually shows all the links that I went to, and that's my grandma. We were visiting her. That's her place, and I couldn't resist showing you this picture since the Queen is in the news nowadays. So that's the Queen. She visited my birth town of Udaipur. I wasn't born then, and that's my grandma right there in the middle, looking straight into the camera. That's it. Thanks for listening. Thank you.
That was so cool, Surabhi. Thank you. Wow. Did some of those buildings display the pink paint from the Prince of Wales visit that you showed on your early slide?
Yes. So in 1876, everything was painted pink. So it's called Pink City now.
Oh my God. Wow,
Yeah.
those instruments are all in fantastic condition, or have they been patched up, do you think?
I think in 1901 or so, there was someone who took care of these instruments, and since then they have been taken care of.
Wow.
But in other observatories like Mathura is no longer there. It's just gone. And the others are not that big, although the Delhi one is kept well, but it's a smaller one. And the others are just okay. I think Ujjain one is also worth a visit, but it's not that big. The Jaipur one was the grandest because that was his hometown. That's where that was the Jai Singh's capital.
I always wanted to visit that place. I've read about it for years.
Oh, you should.
Yeah. Is it possible to, I assume they close at night. Is it possible to take a tour at night and actually see the instruments under a night sky?
I don't know. Maybe a special permission.
If you know somebody.
Yeah.
Well, we know
find
somebody.
out.
We know
I mean-
somebody whose grandmother met the Queen.
Yeah, I think Surabhi's grandmother could work this out for you.
Maybe.
Oh, it's really cool.
But if you are visiting, let me know. Because I have like hundreds of relatives out there in Jaipur.
Fantastic. Thank you. Thank you. I'll ask you to go ahead and release your screen.
Yes. How do I even do that?
What year were you there, Surabhi? A couple of years ago?
2016.
Yeah. Okay. Beautiful. Wow. That is so cool.